you very much for that introduction. I'm very happy for this invitation. Very excited to meet you virtually, and I met you at Northwestern. And today I want to talk a little bit about some of the work that we've been doing at Northwestern, and mainly with some of my collaborators in John Rogers' group. So today I'll talk about the work I did with Dr. Yixin Wu on drug delivery devices, and with Professor Jeong-Sik Choi now Yonsei University on sort of like bioresorbable pacemakers, how kind of like ties together in this field of mechanics and bioelectronics. So kind of like the outline for my talk, first I'll focus on drug delivery with electrochemical bioelectronics, kind of like what are these platforms, how do we engineer them, and most importantly, from the engineering perspective, how do we control them, how do we design them, what are the parameters that are key to ensure that we have, or we deliver the drug in time, that we have the right amount of volume at a specific times, and we can control the flow rate. And how do we can program the delivery based on mechanics models. So first, some of you may be familiar and probably have used already one or multiple examples of drug delivery systems. So these range from systemic delivery, where we have pills or injections or patch. First, the idea is to deliver the drug to a specific location, and then it will eventually reach its targeted location. And this has its benefits and its, I guess, disadvantages. And some of them, or most notably, might be like the side effects associated with some types of drugs. And another one is targeted delivery. In this case, you can think of a nasal spray where you put it directly in the area affected, or like kind of an inhaler where you're targeting the delivery to a specific location that needs it. An area of interest in targeted delivery, for example, is cancer therapy, where you have high toxicity and severe side effects that go along with the systemic treatment, and you can potentially avoid them by kind of like targeting the specific site directly. Now, for brain cancer, for example, you can use something like biodegradable implants, where you place your implant in the specific location of the brain and then kind of like diffuse the drug through, or to like have the treatment being localized. Now, of course, this has a lot of challenges like poor penetration of your implant, invasiveness of the tumor cells, so it kind of depends on the stage of cancer that you're in, and you can't sort of treat all of them with the same idea, and you have kind of like low diffusion or hard diffusion in the brain. To kind of give an idea of why we might be interested in treating things locally rather than in the entire system. Now, in the area of bioelectronics for neuroscience studies specifically, we're interested in engineering systems that can help us achieve certain goals. One might be to record neural activity, but also deliver drugs. So in the past decade, there's been some development of this type of technology, where here you can see a little animal or a rat mouse friend with a headset. So the headset, it's implanted into the brain and it's recording neural activity. This is battery operated. You can only sort of do a single type of experiment. In the case for the system on the left, you can only record electrical activity, and some of them might be limited for a single time use, or you might need to recharge them. So it's not very feasible to be like implanting and then removing the implant from the animal. In other cases, you might have fluidic interfaces along with it to deliver drug. But here in this case, you might need an external reservoir that's connected and wired to your animal, and you're restricting some of its natural motion while we're performing some neuroscience studies of interest. So the idea is, can we combine kind of these interfaces while also offering volume and flow rate control to know how are we delivering the drug, when are we delivering, and how we can control it. Now, in the last couple of years, there's been some progress in bioelectronics for targeted delivery from John Rogers' group. Here in the figure on top, we have a device that sits on the top of a brain phantom. So here you have a device that's indicating that it's operating. So we have a little red LED here, and you're delivering light and drug simultaneously. So you can combine two types of experiments, one for pharmacological experiments and another for optogenetics within a single device. This device is wirelessly operated, so there's a nearby antenna that sends a magnetic field, and then you have a coil that harvests this energy and then powers the electronic components. And then not only for the brain, but you can target other areas of interest. So for example, if you're interested in treating the peripheral nerves, you can place your device nearby in that location, and you can guide it through a series of soft microfluidic channels and then implant the device specifically in the area that you want. And this offers unrestricted animal movement, because you're not sort of constraining its movement by being wired to an external device. It's wireless. You're providing the energy from a nearby antenna. It's battery free, so you kind of like reduce the overall weight of your device. you can combine types of experiments from drug and light and also refillable. So you can run different experiments at different times without the need to replace the entire system. So for example, here, if you're interested in having, your first experiment for the first delivery, you're operating your system, you're sending your fluid, in this case, the yellow one, and then kind of like an orange one for 2 different probes. And then at a later stage in your experiment, you send the green one and then kind of like this red or maroon one. And just to give you a sense of the scale, this system sits on the top of the head of the mouse, and this arrow bar is about 1 centimeter. So here the challenge is we have volume and flow rate control. What are the key parameters that come into play in this kind of engineering system that sits or that's intended to deliver drug into the brain? So let's look at how the system actually works. So for the working principle, it's wireless. What we mean by this is that if we have our mouse that moves freely inside a cage, you can wrap the cage with a transmission antenna, and then you'll generate a magnetic field. And then from this magnetic field, there's an NFC coil. NFC stands for near field communications, that harvests the energy from that antenna, and then is used to power the electronic platform that controls the delivery and the pumping system of your device. So here has some guided wires that go directly into the brain, and then you can deliver the drug. And you can do this for multiple experiments and multiple animals. So for example, here, this animal on the left shows that on A1, this animal has the device operating or is turned on, and then A2, animal 2, it's off. And you can see this red wire right here corresponds to kind of like this green wire right here. This is the antenna supplying the power. Now for the pumping system, I think this is kind of like the interesting part where we have different types of physics going on. Just to give you an idea, this pumping system is one of these reservoirs right here. So in this image here that's exploded view, you have 2 reservoirs, but you can analyze each reservoir separately because they're just identical. So we analyze in one, kind of understand how the delivery happens in one of them. So here we can take a look at kind of like a cross section of our device, and we have a substrate shown in brown. And then on top of the substrate, there's a set of interdigitated electrodes that's shown in yellow. And then there's an electrolyte chamber shown in blue. So this electrolyte for this purpose of this analysis is water, but you can sort of select the electrolytes that you prefer. And then you have a separation between 2 chambers, and you have a flexible membrane. Here's a polymer membrane shown in purple that sits on top of the electrolyte chamber and separates the drug chamber and the electrolyte chamber. And then the drug chamber sits on top of it, it's shown in pink. This is the volume of drug that you're interested in delivering to the brain. Sorry, to the target location, not necessarily the brain. And then you have a set of microfluidic channels that's shown in gray that guide the drug through from the system to your target location. So in this case, target location might be inside the body. Now, when you initiate the delivery, you're supplying electrical current to your electrode. So you're initiating an electrochemical reaction. You're generating gas. So in this case, you have oxygen and hydrogen gas that pressurize the bottom part of your flexible membrane. Then they pump or push the drug from the drug reservoir chamber through the microchannels and into your target location. So here, there's a set of parameters that start to appear. We have pressures, we have currents, we have temperatures, kind of like understanding why do we need to care about these parameters and which ones are more important. So a little bit of summary here, we have the electrical current that flows and then initiate an electrochemical reaction where the gas increases the pressure inside the electrolyte chamber, and then it deforms the flexible membrane and pumps the drug. So we have different contributions from different parameters. First, we have the influence of the environment that can be the area of interest that you want to target. In this case, might be the brain or the muscles or some other organ of interest. Then you have the viscosity of your drug mu, and then you have gas, the temperature parameter here due to the gas formation. Then from part of the microchannels, you have the contribution from the width, the height, and the length of the microchannel, geometrical features. And then from the flexible membrane, you have different parameters. One of them is going to be the thickness of your membrane. The other one is going to be the radius of your membrane. Then you have the Young's modulus, Poisson's ratio, and then very important, the stress-strain relationship of your membrane when you're applying this pressure. And then lastly, you have the coil antenna. This is going to be the electrical energy, or sorry, the amount of electrical current that you supply to your electrodes. So it's about 12 parameters, but we're interested in understanding which ones play a more important role and which ones to change depending on what type of device we're interested in making. So going from mechanics analysis, we do some dimensional parameters to obtain a scaling law that can help us understand what parameters control the delivery. So first, we can analyze a flexible membrane. So here we have a picture of the flexible membrane. You're applying current, and then you're pressurizing the bottom part of the membrane, and it deforms into this shape of a spherical cap. Now, the induced volume V of the flexible membrane is due to the net pressure. So it's P minus P drug. So this is the pressure differential at both sides of the membrane. And this is characterized by the function FV. And this depends on the modulus and also on the stress strain curve of your device. Then if you have a very small deformation, the deformation, you can derive this function analytically from plate theory, and you'll find that your pressure term here, you have pressure on one side, is linearly proportional to the volume. And the coefficient in front of this volume, it's given by its geometrical and modulus parameters. So this is derived from plate theory, and this is just a linear relationship between the pressure and the volume. So you can use a calculator to actually compute this equation, because you will know kind of like all the parameters on your problem. But more interestingly, in general, when you have nonlinear elastic deformation or larger deformations, you might need to rely on some sort of finite element analysis to capture the actual deformation of your membrane. You might need to use a computer in this case to kind of like obtain your pressure curve based on the flexible membrane deformation. Now, in this case, I'm showing it here as the shape as a spherical cap, which means that the slope, if we think of it and difference between bending, the slope at the ends is now no longer zero. Then the contribution from the microchannels, we can sort of quantify the pressure drop between one side of the microchannel and the other one. That's given by this relationship right here. That gives us the drug viscosity and the length, as well as the flow rate of the drug through the microchannels. And then it has a geometrical factor based on the cross-sectional ratio of your area. And this quantity is, you can change it for different types of microchannels if you have different types of cross sections. So kind of like taking from this paper, and we can obtain our pressure from equilibrium. So if we assume that we have a square cross section, we can compute our pressure P that is going to be equal to the function function V that comes from the contribution from the solids. Then we have the influence of the environment, and then lastly we have the contribution from the fluids. So if we take our governing equation, now again, here we have the same pressure from equilibrium, but we have to still consider the gas generation rate. So this comes from the electrochemistry part of generating the bubbles. Now in this case, I'm assuming that N dot, this is going to be your rate term, is given by 3/4 I, where I is the electrical current and F is Faraday's constant. Now this term 3/4 comes from the fact that we're using water as an electrolyte. So this term is going to be this ratio is going to vary depending on the type of electrolyte. And we're also assuming that we have a sort of 100% efficiency rate, which might not be the case for the real experiment, but for the purpose of this assumption, we're kind of like, this is how we're capturing the electrochemistry part at the beginning of the modeling aspect. Then if we integrate over time, then we can get the total amount of gas generated over time. So we have the same rate times our time variable. Now, if we put these two equations into our governing equation, which would be the ideal gas law, that's going to be PV equals to nRT. We have our volume term here, and then we have our pressure term that is given by the solids, the fluids, and the environment. And then we have our N term here given by the total gas rate, and then we have our variable T. So here we have just to remind you, the contribution from the function FB has influence of the membrane geometry, but also the membrane material, so the membrane elasticity as well. And this equation, you can solve it numerically using the initial condition that at time 0, the volume must be 0. But for the purpose of this analysis, we don't want to solve it numerically, because we're interested in finding an analytical model or a scaling law that can help us understand, okay, if we vary the environment, what's going to be the impact? If we vary the elasticity, what's going to be the impact? What if we change the microchannel direction? So instead of solving it on and on and on and on, we're trying to understand and group these things together to go from a numerical approach to an analytical approach, where we can use perturbation and also membrane theory to derive both the pressure relationship and also how to solve these ODE. So for a scaling law, we introduce the following variables, and we write them non-dimensionally in the following way. So T star, this is going to be our non-dimensional time variable. It's going to be equal to the time, is our time variable. And then and then we have a coefficient in front of the time with units of 1 over time. So in this case, this term groups the electrochemical part. We have the influence of the current, we have the membrane modulus, thickness, and ratio square. So this gives us units of 1 over time. Then our non-dimensional volume, we normalize it by the radius of the membrane cube. And in the same way, we normalize our function or pressure function by the radius of the membrane over the modulus times the thickness. So we have here non-dimensional coefficient, and then we multiply it by, sorry, we have this geometrical, and then we multiply by this pressure function here. So we go from having our governing equation looks like this. This is our first order ODE to a scaling law that can be written in the following way. So all the star parameters mean that this is a non-dimensional equation. And we can quickly identify two terms that are highlighted in red. One is the microfluidic resistance. So this is a very important term, and it groups about 9 of those 12 terms that I mentioned previously. We have the influence of the microchannels, the length of viscosity, we have the temperature, we have two constants, then we have the radius of the membrane square divided by the modulus square, the thickness square, and then the influence of the current. And then on the other side, we have the influence of the environment. So this pressure term is also normalized in the same way that our non-dimensional function. So we have the radius over the modulus times the thickness, and then we have our pressure, our dimensional pressure here. So now these two parameters control the delivery process of our system. So in our scaling law, we go from about 12 parameters to only 2 that group geometrical, flexural, fluidic, electrical, and environmental terms. Now, how do we solve or what is the solutions for ODE? Now we notice that here we have to make a key assumption, and that is based on the values that we measured from the experiments. So here, if we go back to our terms, we can actually compute what these parameters are going to be based on the device that we have. And we find that M star is a small parameter as compared to P0 star. So this means that M star is 2 orders of magnitude smaller than P0 star. So that means that we can use perturbation analysis to solve our scaling law. So first, we can find our solution without the flow resistance. So we assume that M star is 0. But when we do that, we eliminate this term and we take away the rate variable here. We take away our dVdt term. So this term right here gives us time on one side. So this is time. It's equal to volume. And we have these two terms here, volume times pressure and volume times pressure based on the membrane. So this is the solution without the flow resistance. And this gives us the time it takes for the membrane to overcome the external pressure and the form. But then from perturbation, we can obtain our perturbation term, which is T bar. So we have M star T bar star, and we can derive this term and we obtain a term that looks like this. So we have M star in the front, and then we have our flow resistant term. So here we have V star over, and then we have a derivative term plus P0 star. So this is derivative with respect to volume, not with respect to time. So on one side, you have all your time terms. On the other side, you have all your volume terms. And this gives you the time it takes for the drug to travel through the microchannels into the target location. So you have T equals A, where A is going to be your solution without flow resistance. This is the time it takes for the membrane to deform. And then B, which is the time it takes for the same amount of volume that you're ready to deform to travel through the microchannels into your target location. So if we write this equation dimensionally, we can find that we have our time is equal to, and then we have the contributions from the electrochemical part, then we have the contribution from the membrane, the contribution from the environment, and we have, lastly, the influence of the microchannel. So we have 2 time terms, and they're adding here. So kind of think of, okay, these times evolve simultaneously. But just to remind you, we still haven't discussed how to solve this function FB. We have a nonlinear elastic arc deformation, but we can use finite elements at this point to solve this equation. So we'll call this solution semi-analytical. So we have used perturbation to solve our ODE, but we're still going to use FEA to find our function FB. So if we take a look at volume and flow rate temporal curves, we can see that when M star is very small, that means 2 orders of magnitude below our other controlling term. So we have 10 to the minus 4, 10 to the minus 3. The numerical and semi-analytical solutions agree very well. And we don't have any parameters fitting here. So we're just doing the semi-analytical and numerical and semi-analytical models here. And then if you take a derivative of the equation that I just showed you, so instead of thinking of volume, you think of dV/dt. So this will be flow rate versus time over time. We can see that the red curve and the blue curve follow this kind of like incremental step. Then they reach a maximum flow rate, and then it gradually decreases. And as you go a further order of magnitude above, in this case would be 10 to the minus 2, then you can start to see how these curves no longer align. This is because of the assumption that we made that M star was a small parameter. And this assumption is based on sort of also the physics of the system, because if you have a very, very small, if you have a very, very large microfluidic resistance that's impeding the flow, you can potentially block your microfluidic channels or have other sort of issues with your device. So it's kind of like makes sense that you don't want your microfluidic resistance to be that much higher or even comparable in terms of dominating the delivery as your other controlling terms. So it kind of makes sense that you can keep these M star orders of magnitude below your other non-dimensional. So if we compare it with some of the experiments on the device that I showed you before, this is for the drug, for the delivery in the drug in the brain, we can quantify the maximum flow rate. So this is going to be the peak here on the flow rate versus time curve. And we can see that for effective currents that range from about 0.1 to 0.6 milliamps, we can see that the prediction for the maximum flow rate is it's okay. It's good actually at small range of the currents, but for larger currents, you might have some additional bubble generation that might affect the effective current that's going into the device. So we end up a little bit over predicting in the numerical aspect by a few percent change. But if we take a look at the flow rate versus time, we can see that actually the flow rate versus time that's just recorded from the experiments until the point of the maximum flow rate, which is the quantity that they care about, it matches very well. This is for a current of about 0.3 milliamps. So this modeling experiment right here, we have very good agreements, particularly at that initial times where the maximum flow rate occurs. Now, if we take a look at what's happening in our membrane, we have bending versus stretching dominated deformation. And we can sort of separate these two areas in the following way. So when you have bending dominated deformation, it's going to be small deformation. You can think of it as when the vertical displacement of your membrane is much smaller than the thickness of your membrane. So here you're going to have bending dominated deformation, and you can sort of derive what's the volume condition for you to have this type of deformation. But more interestingly, for these kinds of devices, you're interested when the deformation of your membrane, the vertical deformation, is much larger than your thickness of your membrane. You can also derive that condition based on the volume of a spherical cap, where you will have a stretching effects also in play in the membrane. And for anything in between, you can kind of just use like finite elements to calculate what the stress strain curve for your, what the pressure volume curve for your membrane is going to be. So if we take a look at stretching dominated, this will be a finite deformation. We have the volume of a spherical cap. We have two competing pressures. The pressure that's generated from the bottom, this will be from the electrochemical reaction, and then the pressure on top from the flexible membrane. And then here we introduce this parameter phi. So this is the angle that tracks the deformation from flat to the shape of a spherical cap. So this angle phi tracks the deformation from flat to the shape of a spherical cap. And we can find different relationships. First one is going to be the strain on the membrane as a function of phi. We can derive the strain on the membrane. It's given by sine phi over phi. It's going to be 1/1 plus the strain on the membrane. There's our first relationship right here for what's the strain as a function of this angle phi. And then we can derive our relationship for the volume based on the geometrical features of the spherical cap. So we can find what the height is going to be as a function of phi, and then also what the volume is going to be as a function of phi based on the height of the membrane. And we find out this relationship right here. So we have volume on one side of the equation, and then we have phi on the other side. So we have about two terms, but all of these terms only depend on phi. So this only evolves as you're increasing your angle phi. And then you have the pressure relationship that comes from equilibrium at the membrane, where you have this pressure differential, and then you'll have we assume that the material is incompressible, so we can calculate what the stress or what the pressure is going to be in your membrane. And you can write your equations in the following way, where you have your function FB is going to be equal to P minus P drug. So this is going to be the pressure differential at the top and bottom of your membrane. And then you have this term right here that has a geometrical factor, h over r0, and then you have your phi terms, and then you have a sigma term. Now, these two equations are parametric equations. They depend on the angle phi, but we can solve them simultaneously and plot them together, and we can obtain what our pressure versus volume function is going to be. And then from our pressure function, we have sigma, and this sigma is going to be the true stress. The true stress that depends on the material model or the stress-strain relationship curve of your polymer membrane. So, for example, if we assume that our membrane behaves linear elastically, in this case, we're saying that the stress is related to the strain by the equibiaxial stiffness of your membrane. Now, this is kind of like just a very basic assumption to show how we can just derive a very simple approximation of the membrane deformation. So here, if we take a look at the images on top, we see that at time 0, we have a flat membrane, then time 20, time 60, time 80 seconds, it'll eventually evolve into this spherical cap. And if we derive our equation we assume that's linear elastic when we have a very, very simple solution for our pressure volume relationship where it's 128 over 3 pi cubed times this volume to the third power. So it's kind of this power relationship. But in reality, we'll have some hyperelasticity in our membrane, and we can solve it by using some generalized hyperelastic model where we have our contributions from the membrane, in our function that is given by, in this case, it's going to be like the Mooney-Rivlin model, where we can see that finite elements, in this case, the continuous red curve and then membrane solution agree very well. And it makes sense that the membrane solution is below the FEA because you're neglecting the bending effects of your membrane when you're using the membrane solution. So it kind of like goes it goes below the FEA. But more interestingly, let's say that you have some material and you have some data for stress and strain. So you have some experiments, you have your material that's going to be SBS. So this is a block copolymer material. You test it and you find what its stress strain curve is going to be. Then you can use Marlowe model. This is like a hyperelastic strain energy model where the strain energy function is built directly. It's built from the first invariant of your model that's given by the stretches and given by the stretches written right here. And this is, you can use this for sort of any polymer material that you want to fit into your hyperelastic law. So this is kind of like more interesting if you have kind of like a material and you can fit its mechanics deformation, then you can also find what the function FB is going to be and you build it directly from your material data. So here you can calculate what the stress is going to be. This is given by 2 over, you have the derivative of your strain function with respect to the first invariant, and then you have a function of the angle phi. And then you have your volume that's going to be also given by the angle phi, and you can plot them together. So if you have your stress versus strain, then you'll find what your function pressure versus volume function is going to be for analytically based on the experimental data that you have. So then now we have found a way to model our function FB if we have some generalized hyperelastic law, or if you have some experimental data for your particular membrane that you're interested in. So you can sort of solve this equation using a calculator now instead. And this is, and here I just want to highlight the implications of selecting a correct material model, because here if we have, your function pressure, you have pressure versus volume, and you're quantifying the amount of pressure that it takes or the volume that's going to deform at a given pressure. If you assume that your membrane is going to be linear elastic, you can see that at the beginning of the deformation, when the deformation is small, of course, these two agree very well. But as you're increasing the deformation, this linear elastic model gets significantly stiffer. So you need a large pressure to deform for a set amount of volume, where in the real case, where you're using the experimental data in the Marlowe model, that's not the case. So you need much, much, much smaller pressures to achieve the intended volume. So you will end up over predicting the amount of time it's going to take for you to deliver, let's say here, 1 unit of non-dimensional volume. You'll get it at around 0.4 non-dimensional time units. But if you go with linear elastic, you probably, you go 1 or above. So you're kind of like over predicting it. So it's pretty nice to check that if you have, your data, how it relates to the actual experiment. And we can compare it with some of the experiments that they've done. So this one is going to be like Here we're plotting the fluid velocity and a cross-sectional channels. This was done by one of our collaborators in the paper. And here we are comparing the experimental measurements that's shown in gray, and then two models, the semi-analytical model and an analytical model with model. So here, what's interesting is that first, the semi-analytical, we can see that we end up a little bit over predicting the behavior here. And I think this might be an issue with kind of like channel compliance a little bit. So if we have some very, very high flow rate or very accelerated flow rate at the very beginning, we might end up expanding the channels. So the flow rate is going to be lower. But we kind of like thinking about it to see if that is actually the effect that's happening on all the channels or for all the operational modes. But in the end, we end up being very, very close to the maximum flow rate, which is kind of the quantity that they care about. This is because you don't want to impose excessive stresses as you're delivering your fluid to the specific locations that might end up damaging soft tissues. And then here's semi-analytical model. You can observe this drop right here. This is because at this time, about 20 seconds, this is the time that the membrane has finished expanding. So the membrane doesn't expand forever. It hits a certain point where it hits the top surface of the drug reservoir, and then kind of like the pressure drops there, as you can see, and the flow rate also drops there, typically because of that stop. But in the analytical model, you don't account for that. You don't have that, so kind of like you can see how it just goes and it doesn't drop, but kind of predicts the maximum flow rate well. And kind of like the idea here was to see, okay, if you can use something related to this for some autonomous emergency responder to sort of tackle a problem right now in society, they were thinking of doing it for the opioid epidemic. So for the past decade, we've seen an increase on opioid overdoses in the US, where in 2020, we hit about 68,000 people that died from any opioid-related overdose. And just for comparison, you know, Soldier Field capacity here in Chicago is about 61,000 people, so about 7,000 more people than you have a full stadium. And the idea here was, okay, if you can monitor, for example, blood oxygen levels, and then you can trigger the emergency response and send the drug through drug delivery channels when you need that drug. How do you engineer this system so that you can get it there efficiently and also timely, because for an overdose, time is of the essence. You need to administer the drug within a timely period. So we use we can use our model. We can use what we studied on how do we program the delivery based on our time versus volume curve that's controlled by two parameters. In this case, it's going to be our pressure and our microfluidic resistance, where we scale up. We're scaling up our device from uses in small animals to humans. But of course, it's going to be kind of like a larger step in the future. But in the end, you can sort of like answer the question. You say, okay, if you need to deliver 120 microliters of life-saving medication in your modeling, you can sort of estimate it a little bit. It would be about 95 seconds or a little bit, a minute and a half. And what parameters you need to take or optimize to sort of shorten that delivery time frame. And then in the topic of putting things in the body and playing with the human body using electronics, I also would like to discuss a little bit about bioresorbable implants and what are these devices. Why do we need to care about if we're dealing with the human body, and what are sort of the implications of defining these kinds of technologies for use? And this was work done with Young-Sik Choi. So it's very, very nice work on how do we engineer these kinds of systems. And the motivation is to sort of change a little bit the way that we provide temporary aid after heart surgery. So heart disease is the leading cause of death for men, women, and people of more racial and ethnic groups in the United States. And we're aiming to wirelessly provide temporary aid to the heart during the post-surgery process. So right now, the way you kind of like pace the heart after you have a surgery, you have sort of like external generator. You have some LEDs that connect to the heart, and then you sort of like help it for a specific period of time once it's healed post-op, and then you pull out these devices. So that may be some sort of strain into the tissue as you're like pulling them out, and kind of like it's not very good to have patients go in for surgery, then again to remove stuff. It's kind of like minimizing that that interaction for the patients, and if we can do that using some materials and mechanic solutions. So the idea is if we can provide a wireless pacing platform where you can, deliver wireless energy to a sensor that it's implanted on the surface of the coil, on the surface of the heart, and then will eventually bioresorb after surgery without the necessary to remove it using also surgery procedures. So kind of like the outline of these devices, you have 3 different separate units that work together. You have the powered harvester here. So you have a coil here that harvests energy from a nearby supply. Then you have a stretchable interconnect. This is one that allows you to manipulate, operate the system, and it increases the elastic stretchability of your system for specific applications, whether it is to put it on different surfaces that have nonlinear deformations, but also to allow it to manipulate or bend or twist as you're implanting the device. Then you have kind of like your pacing ability or your final electrodes that are actually in contact with the heart tissue. And for the bioresorbability of aspect, we can see here that, at day 0, we have a full complete device, and at day 20, this device is submerged on some aqueous solution. Day 20, you start seeing how the device eventually disintegrates over time. This process is governed by a reaction diffusion process where you have the diffusivity of water on your materials, and then you have the influence of how's the concentration changing over the thickness of your materials. Then you have a reaction term here that affects the chemistry of your material as it's water, it's coming in, how it's reacting with the material. Then, of course, it's a transient process. So you have kind of like your time derivative of concentration over time of different parts of your material. You can see here for the molybdenum. So here, I wanted to mention that the conductive elements are made of molybdenum, magnesium, which are materials or metals that you typically have recommended on a vitamin or daily diet for your daily consumption. So these are not materials that are not familiar with the human body. They can see that as a function of time given in days, how the resistance changes, meaning kind of like how they sort of become no longer useful. So you can tune the material to dissolve over a specific timeline of interest, depending on how much time you need it to operate. And you can optimize the serpentine mechanics. So if you take this sort of horseshoe design, that you can get the distance from both of them, kind of like fix it and then optimize 2 parameters. One is going to be the angle alpha, and the other one is going to be the distance between the traces. And you can obtain the elastic stretchability. So this is going to be when the material experiences no yield, so all the deformation is reversible. And you can optimize it. For example, here we recommend that your distance is going to be minimized, so you can have about 52% elastic stretchability. That also kind of like increase the angle here alpha to about 264 degrees, so you will kind of like maximize your elastic stretchability. This is important because the device will experience different types of deformation that you can quantify, in this case using finite elements, to kind of like understand what are the limits you can impose on your material, not only when it's operating, but when you're deforming it or putting it in place. If you're holding it with grippers and you need to put it, because you can't make an incision that is like the size of your device. You need to kind of like maneuver it and put it in place. In terms of electromagnetic performance, you're putting things inside the body, but you're also sending electromagnetic energy through your tissues, and you can sort of engineer the outside device as well, not just the inside, because the inside, once you put it in, you can no longer change it. You can sort of like model what the transmission is going to be based on the distances and the geometrical features. And they did collaborated some experiments where you have the skin, different fat, tissues, bone, meat, and kind of like obtain these relationships where the efficiency of your transmission is going to decay with the square cubic with the distance that you're putting in. This is important because you're operating at some depth within the body. You're going to be able to power the device and supply the appropriate amount of energy to your specific system. And then you can also tune the device, so you can target different applications where you have some like adjustable length, where you can sort of increase the serpentine area, but also depending on the application, you can tune the other geometrical parameters. Like if you have interest in like humans or dogs or small animals, you can tune kind of like what the geometrical features of your coil are going to be, and you can quantify based on the operational parameters of your coil. In this case, they're operating at a frequency of about 15 megahertz, and we can sort of calculate all the inductance, capacitance required to make them, to tune them properly so that they're operating there without any trouble. And then we can also study its penetration depths, and this is more on the last part of the electrode, where you can study electrode spacing and understand how the electric field is going to decay on the tissue as a function of distance away from the tissue, depending on the amount of voltage that you supply, and the spacing. You can sort of like calculate the volume of cardiac tissue that is within a certain threshold. So in this case, this 0.2 here is pointing to the electric field has decayed about 80% at this specific distance from your electrode surface. Then you have also temperature and imaging compatibility. So in this case, if you're harvesting energy and you're powering your system to pace the heart, you can sort of you can have an on and off pulse sequence operation, where as you turn it on, you're going to have a rapid increase in temperature on your conductive element, in this case, the molybdenum layer, just because the conductivity is orders of magnitude higher than that of skin. And then you turn it off. So this is a very, very small time period. You can see this decrease in temperature here, and then skin eventually cuts up in this transient process. You can sort of calculate what the temperature of your device is going to be. So you have a very, very small temperature increase here, about 0.035 degrees Celsius at the time image of 0.17 seconds. It's about here when that skin bump increases. And the same for imaging compatibility. So you can put your device in the skin, in a chicken thigh, kind of like image it to see if there's any disturbance or interference with your system. And this is quantified based on how does the device affect the in-plane gradients of your magnetic field distribution, kind of like design it so that it doesn't interfere with any clinical procedures that the patient might need to have. And of course, you have a safety consideration. So here the idea was to sort of come together with all the devices, and if you have some sort of module that is currently pacing your heart, but then you need some sort of additional additional antenna where you can sort of replace, so you can go charge your device and then bring it back again and tune it again. It's kind of like having to recharge this wearable device that you just stick on your skin, and you can calculate what the specific absorption rate is going to be. So this is the amount of energy absorbed over a volume of tissue. And there's a recommended limit by the Federal Communications Commission. So our cell phones have, for example, these limits of energy absorption that we need to be considerate about. And we can model what the absorption rate is going to be for a specific kind of application when we have just one device operating, but also multiple antennas operating as well. This depends on the electric field and also the density of the tissue that you're quantifying. This is kind of like a broad picture of future applications for body integrated devices, where you have a main control module that you can use wirelessly, and then you have devices that can track, hemodynamics or blood properties. You have mechanoacoustic signals. You have cardiac pacing, and also haptic interfaces. To kind of have those devices interface with the body, they're very interesting mechanics. And electromagnetics, so kind of like you have respiration, haptics, cardiac, hemodynamic devices, bioresorbable, and just for comparison, here's the order. You can kind of see what the scale of this device is. Kind of like having mechanics and also electromagnetics on together. This is kind of like the outline of the presentation, where I talked a little bit about drug delivery systems, kind of like the mechanics involved in it, and also how do we engineer this kind of devices, bioresorbable devices, as we go from purely, the math and models for this device, but also some other systems that I found interesting that we put in the body. And with that, I'd like to acknowledge all my collaborators from the theory part, Professor Yanlang Huang, from the experiment, Professor Rogers, and all the collaborators that I've had over my time here at Northwestern. We worked on a lot of interesting topics related to bioelectronics, and of course the Ford Foundation and the NSF for funding my PhD. And with that, I'd like to thank you for listening, and I'm happy to take any questions that you have.